Is this visible to all of you?
Yes, sir.
Okay. So last day we started our discussion on quasi-concavity and quasi-convexity. And after discussing the definition, this was one example at which we stopped. So did any of you give this a try? So we wanted to understand whether the y equals to x cube function is concave, convex, quasi-concave, and quasi-convex. This is what we wanted to understand. Anyone? Okay. So maybe we can try to go through this example first, and then I'll take you to different questions. So the question was for a function y equals to x cube. And if I can just draw the graph once more, so this is your function y equals to x cube. So before actually going on for all the checks, just one thing. Can all of you just tell me what is the definition of a concave function that we discussed the last day? Anyone? How do we write it? What does a concave
Uh,
function mean? Yes?
yeah, means the function of lambda a plus 1 minus lambda b is greater than equals to lambda of fa plus 1 minus lambda of b,
Yeah.
where
Correct.
lambda is less than 0 is less than equals to lambda is less than equals to 1.
Hmm.
And a and b are 2 points in the x-axis.
Correct. This is concave. That is the is above the line. That is how the definition goes. And what is the definition for convex? Anybody? What was the convex definition? Convex function would look something like this. So if you take any 2 points, the line would be above the curve. That means the inequality would just switch. So the function of lambda a plus 1 minus lambda b is less than or equals to lambda times fa plus 1 minus lambda times fb. What was quasi-concave? Anyone? Yes, anybody? What was quasi-concave?
The function of lambda a plus 1 minus lambda b is greater than equals to minimum of function of a or function of b.
Correct. Is greater than or equals to minimum of function of a comma function of b. And finally, the last one, which is quasi-convexity. What would be this one? Anybody?
Func- Function of lambda a plus 1 minus lambda b less than equal to maximum function of a into function of b.
Not into fa comma fb. Yeah. And for all cases, your lambda lies between 0 and 1. So if you look at the graph of this function x cube, what can you see? If you take any two positive values of x, the line lies above the curve. However, if you take any two negative values of x, line lies below the curve. So it is concave, right? So for y equals to x cube, it is concave for x negative and it is convex for x positive. Therefore, overall, it is neither concave nor convex. Okay?
So,
Yes.
in the diagram, how can we say that it is above the curve or below the curve? Means in which respect?
Uh, Above the curve or below the curve in which respect? With respect to the
Mhm.
x-axis.
Yes, means
Horizontal.
if we take x is greater than 0
Yeah,
and take 2 points,
yeah,
okay, it
that's
is we are taking that, yeah. So here we are seeing that the straight line will be away from the x-axis, means with respect
away,
to the curve.
away is the word that you're using, and I'm saying above. Essentially the same.
Yeah, yes, means if we take the curve to this curve, in one side we have the straight line and on one side we have the x-axis,
Okay.
right?
Yeah.
But when we are taking x less than equals to less than 0, we are having the same, means with respect to the curve, one side is the x-axis and one side is the straight line.
Okay. I see what you mean to say, or where the
Yes.
confusion lies.
Hmm.
The direction of my view is this. Okay, Ankit.
Okay.
From bottom to top.
Okay.
All right.
Okay.
If you just look at these small two graphs that I have just constructed, these two, by
Hmm.
concave, I mean it's basically like bending towards the x-axis, and by convex, I mean it is bending away from the x-axis. Right? And how do I
Hmm.
decide that? Because I am viewing it from bottom to top, isn't it?
Okay.
If you are,
Okay.
what you are saying is basically for positive values, you are taking this view from down to up, and for negative values, you're taking the view from up to down. Not that.
Yes.
Okay,
Okay.
it has to be a singular view, either this
Okay.
or that. Okay, you can't change
Okay.
the direction of view, otherwise, obviously, it will change. Okay, I
Okay,
hope
sir.
this makes sense. All right. And if Ankit, there is even the slightest amount of confusion in any, this is a very simple example that we have started with, but in case there is, you have the double derivative criteria, right? So if you take the single
Yes.
derivative, what would it be? This would be 3x square, and the double derivative would be 6x. So you can understand that this will be positive for x greater equals to
for
0
x
and
greater
this will be
than.
negative for x less than equals to 0. Correct?
Yeah.
Double
Yeah.
derivative positive means convex. Double derivative negative means concave. Okay, so you can always cross check even if you are
Okay.
having some confusion. That's always there. Okay, so
Okay, sir.
it
Thank you.
should be a singular directional view. That's the thing. And only in that respect, I'm saying this above, below, and things like that. All right. So
Okay.
the conclusion that we got over here is that the function is concave for negative values, for convex it is positive. That means overall, entire real line is neither concave nor convex. That's the first conclusion for this y equals to x cube curve. Okay, that means now we need to check for quasi-concavity and quasi-convexity separately, because had it been convex and concave, quasi-concavity and quasi-convexity would have been automatically implied. But since it is not concave and convex, so we need to check for that as well. So let me name these 2 points as well so that we are through with this. Okay. So obviously what we need to do over here, we need to take 3 situations. Let's say I'm checking for quasi-concavity. Okay. Since the origin is the point at which it is changing the curvature, we should consider 3 situations. Number 1, we should take 2 positive points and check. Number 2, we should consider negative points and check. And number 3, we should take 1 positive and 1 negative. So let's take one by one. Case A, points A and B. Okay, where f of A is lesser than f of B. In that case, what you can see? What is the definition of quasi-concavity? The functional value at any point in between should be greater than minimum of these two. What is the minimum of fa and fb? It is f of a, right? This is the minimum. So you can see that this is holding for this positive part, because no matter which point you take in between these two, a and b, the functional value will always be greater than equals to fa. Let me write this part. That means mean of fa comma fb is equals to f of a, and function of lambda a plus 1 minus lambda b is always greater than equals to fa for all lambda lying between 0 and 1. Correct? Is this part understood by all of you? If you all can reply with a yes or a no, if this makes sense. From the graph, we can directly understand that. And similarly, if you take 2 negative points, let's say point C and point D, such that function of C is greater than function of D, right? Because function of C is this amount, function of D is this much. So if you take any intermediate point in between, then also the functional value will lie greater than function of D, because this is the minimum point. All right. Function of lambda C plus 1 minus lambda D is obviously greater than function of D. So it holds for these two regions. And if you take, let's say, 1 positive and 1 negative, let's say I take point D and point B, then also the minimum would be function of D. And if you take any point in between this range, A and D, then also it will hold, correct? The functional value will lie greater than function of D. That means case 3 would be to take B and D such that function of B is greater than function of D. Here also it is satisfied, greater than equals to function of D. Okay, So we have taken all possible combinations and we can conclude that the function is quasi-concave. Okay, is this understood by all? If you all can reply with a yes or a no. We just took
Yes,
three
sir.
situations. Others, is it making sense?
Yes.
Now, if we have gone through concavity, quasi-concavity, convexity will be exactly the similar way, right? You can see that that will also hold, right? Can you all understand that? We'll just take the maximum values. So any point that you take in between the ranges, the functional value will be less than the maximum value. That will also occur, correct? So I'm not working out the calculation once again, but obviously you'll take the same ranges and the calculation will change. And similarly, quasi-convex as well. So what is our ultimate conclusion that we get? Y equals to x cubed, the function that we have taken, is not concave, not convex, but it is quasi-concave and it is quasi. Okay, this is essentially the conclusion that we can get. All right. Any questions from anybody? All right. So let's move on. Let me take two other most common examples. The exponential function and the logarithmic function. Okay. Let's draw the two graphs that will help us to understand this better. Just a minute. Yeah. 0, x, y. So the exponential function will look something like this. Y equals to e to the power x. And the logarithmic function would look something like this. Y equals to ln x. So the question remains the same. We want to check for concave, convex, quasi-concave, quasi-convexity. Two things we can obtain directly, right? E to the power x is a convex function, right? Are all of you aware of this? If you all can reply with a yes or a no. E to the power x is a convex function.
Yes, sir.
Yeah. Others, if you all can confirm as well.
Yes.
So if it is convex, then quasi-convexity is automatically implied. You need not check that additionally. That will automatically hold. So that is done. So since it's convex, quasi-convexity is automatically implied. That need not be checked. Okay. But it is not concave, right? Therefore, we will check for quasi-concavity in this case, if it is holding or not. Similarly, for the logarithmic function, we can see that it is concave. That means this function will be quasi-convex, quasi-concave, but it is not convex. Therefore, in this case, we will only need to check for quasi-convexity. Okay. So to check that, what we would do, let's come to the e to the power x function. As you can see, it is consistently increasing. So taking one positive, one negative values won't make much of a difference. So let's say I consider two positive values. That won't make much of difference. Okay. So what do we need to check? This is my function of a, and this is my function of b. What is the minimum of these two? F of b. Correct. So if I take any point in between these range a and b, the functional value will always be greater than equals to fa. Correct. Therefore, the function is quasi-concave. Right. The functional value of lambda a plus 1 minus lambda b is always greater than function of a. Therefore, this function is quasi-concave. Is this logic understood by all of you? If you all can reply with a yes or a no. Making sense?
Yes, sir.
Yeah. And similarly, for the log one, again the same thing. We'll be taking two random points over here, a and b. This is my function of a, and this is my function of b. The maximum of these two is function of b in our case. So if you take any point in between this range, the functional will always be less than equals to fb. Therefore, the function of lambda a plus 1 minus lambda b is less than equals to function of b, which is nothing but the maximum of these two. I think we should mention it. And over here, this is equal to minimum of fa comma fb. Okay. Therefore, quasi-convex. Okay. Therefore, ultimately, what is e to the power x? It is convex, which means it is quasi-convex, and it is quasi-concave. And similarly, the log function is concave. That means it's quasi-concave, and it is quasi-concave. Sorry, convex. Okay. This is the ultimate thing that we get over here. Any questions from anybody? Dia, you were asking anything? Okay. Let's take one more question over here. Let's consider the function y equals to x squared. Okay. How does this function look like graphically? Can anyone tell me? What shape is it?
Parabola?
Correct. It's parabolic shape. So given this function, we want to check if it is quasi-concave, quasi-convex, and the four things basically. So x, y, 0. So it's basically the standard U shape. Sorry. Yeah. So this is my y equals to x square. So one thing which we can directly see from the graph is it is convex. That implies that it is quasi-convex, right? Which we can directly understand. But it is not concave. That means we need to check for quasi-concavity. All right. Now check, understand this over here. If I take any 2 points, let's say on the right side, that means two positive values, then will it be quasi-concave? What do you think? If anyone can just give me a guess answer as well. If I take two positive values, okay,
Yes, sir. I think it is. It will be quasi-concave.
it will be quasi-concave, right? Because this would be the minimum value, and any point that you take over here, the functional value will be greater than that. So that will suffice. And similarly, if you take any point, any two negative points, then also it's fine, right? Then also this condition will hold, correct? Making sense? But
Yes.
what if you take one positive and one negative? And let me just tell you which particular situation I'm talking about. Let's say I'm taking the point 2 over here. So x square is 4, and on the negative side I take minus 2. All right. Let's say I take these 2 points. Let's say this 2 is my point A and minus 2 is my point B. So let's take this example. A is 2, B is minus 2. So function of A is equals to function of B, which is equals to 4. Correct? So for quasi-concavity, we want to find out the minimum of FA, FB, which is minimum of 4, 4. It is simply 4. Right? If you take any point in between this minus 2 and 2, will the functional value be always greater than equals to 4? No, right? If you take 0, the functional value is lesser than the minimum. Correct? Can you see this? If you take any point in between minus 2 and 2, the functional value is not greater than equals to the minimum. The minimum is 4. Right? The function is bending down over here in this way. Therefore, for therefore the functional value of lambda a plus 1 minus lambda b is not greater than equals to minimum of fa comma fb. Correct? For this case. Therefore, it is not quasi-concave. Could you follow this example? I request all of you to reply with a yes or a no. This last part. Does this make sense?
Yes, sir.
Others?
Yes, sir.
Okay. So if this quasi-concavity condition is violated for any one set of points, we can straight away conclude that the function is not quasi-concave. Okay. That's the plain and simple thing that we are seeing over here.
Sir,
Yes, Ankit?
uh, sir, here means, do we have any geometrical interpretation or geometrical intuition of quasi-convex and quasi-concave? like which we have in for the concave and convex, that is point joining the straight line joining 2 points will be above and below. Do we have
Uh,
similar thing for
concave is a similar chronology, right? Like over here, um, let's say I take this graph, okay, this log graph. This log graph, we are checking for quasi-convexity, right? Correct.
yes sir.
So the logic
Mm-hmm.
behind quasi-convexity is that if you take any set of points in a given range, the functional, so if you take any set of values within a given range, the functional value will be less than equals to the maximum. Okay, that's
Yeah.
the geometric interpretation, nothing more than that. You can construct this
Mm-hmm.
line, but that's really not necessary. That's directly coming in for concavity and convexity. Okay, like apart from this,
Okay.
there is no extra geometric interpretation, so to say. I don't know if you're asking
Okay.
something else, but geometric interpretation is this only, nothing more than that. You just take
Okay.
points within a given range and try to see whether the functional value is less than equals to max or greater than equals to mean. That's the only thing that we're interested in.
Okay. Okay. Thanks.
Okay. So this function that we took over here is only concave and sorry, is only convex and quasi-convex, but not concave and quasi-concave. Right. So from these examples that I took, we have a very generic result that I wanted to share with you all. Are you all aware of this concept of monotone functions, or let's say monotone increasing and monotone decreasing functions? All of you, can all of you please confirm if you're aware of this?
No, sir.
Monotone increasing function means the derivative at all points is positive. That means the function is always increasing for every point. And monotone decreasing means the function is always decreasing. Okay, check these examples that I just showed you. X cube, it's always increasing. The first derivative will always be positive. E to the power x, it's always increasing. Log x, it's always increasing. But this parabola that we took is not a monotone function, right? It is decreasing for negative values and it is increasing for positive values. Correct. So monotone functions is basically, if it's a monotone increasing, then the derivative will always be greater than zero. If it's monotone decreasing, then it will be less than zero. Let me put the equality as well. That will not bring any harm. And if we want to write the condition without using calculus, then we would write monotone increasing in this way. If we consider 2 points such that a is less than b, then function of a is less than function of b for all a comma b. Monotone decreasing means if a is less than b, then f of a is greater equals to f of b for all a comma b. And if all of you want, maybe you can take down a small diagram to accompany your results. So monotone increasing means something like this. Monotone decreasing means something like this. For every point, it is decreasing. Okay. That means the sign of the derivative remains unchanged. All right. So the result that we are going to talk about over here is monotone functions are always quasi-concave and quasi-convex. Okay, got it. This is the important result that we can use, and all of you can use for your entrance exams as well. If the function is monotone, then it will always be quasi-concave and quasi-convex. You can use the derivative criteria to check for that. You can use this criteria that I wrote, or if possible, if you know the graph of the function, you can draw the function and check. Okay, whichever one suits you, you can do that. All right. Any questions from anybody? Okay. One more thing in addition to this that I want to mention over here, the second thing over here, are all of you aware of the concept of monotonic transformations? Yes, you might have studied in your microeconomics, monotonic transformations of utility functions. Anyone? Perhaps you all have forgotten. Let me just recap this. From here also we can get another interesting result. Consider, let's say, the utility function. Something like this. X to the power half, y to the power half. The Cobb-Douglas function. If I take the log of this utility function, what would we get? Half of log x plus half of log y. Correct. This function is a monotonic transformation of u. Right. What do we mean by a monotonic transformation? It is basically a functional transformation that keeps the order or the ranking of the bundles unchanged. Okay. If I define, let's say I define this function as, let's say, u curl xy. Okay. Let's say I define this function as this one. So the monotonic transformation, we were writing the definition. It's a functional transformation that keeps the order of the bundles unchanged. That means, let's say we consider two bundles, x1, y1 and x2, y2, two bundles of commodities. If under the u function, if the utility is greater than equals to the utility from the second bundle, x2, y2, then the order remains under this transformed function. Okay, can all of you understand this? If you all can reply with a yes or a no. Is this understandable?
Yes, sir.
Yeah,
Yes, sir.
correct. And if you remember, we have done this, it's been quite some time, I understand, that if you take the original utility function and try to work out the consumer demands for a good x and good y, that will be exactly the same if you take the modified function, right? Because the ranking is remaining unchanged. So that is why consumer preference as represented by u is exactly the same as represented by v. Okay, so the very monotonic transformation that we take, right? Log and exponent, so to say. So monotonic transformation is basically, if I just write it down technically, consider a function fx. Okay, such that fx1 is, let's say, less than fx2. Okay, and consider a function g. Then g will be a monotonic transformation of f if g of x1 is also less than equals to g of x2. Okay, the order of the points or the order of the coordinates remain unchanged. The functional values might differ. That's not the case. Only the order will remain unchanged. Okay. So so if you have understood this, let's come back to what I was wanting to say regarding this and the quasi-concavity part. A monotonic transformation preserves the quasi-concavity and convexity, quasi-concavity and quasi-convexity of the function. Okay, but this is not the case for convexity and concavity. That might change, but the quasi-concavity and quasi-convexity properties will remain unchanged. Okay, this is another add-on thing that comes up. All right, let's take an example to understand this. Suppose I consider a function fx as root x. Okay, so how does the function root x look like? Can anyone tell me? What is the graph of root x look like? Yes, anyone?
Horizontal hyperbola
Can you repeat, Ankit?
means,
I couldn't hear you.
horizontal hyperbola means with respect to the x-axis. The axis will be the x-axis.
Okay. It's concave, right? That's enough. This is this curve. Okay. If I take cube of this function, let's say, then it will be a monotonic transformation, right? As you saw in this curve, that it's always increasing. So it's a monotonic transformation. And if I name this as my gx, the modified function, then what is gx? X to the power 3 by 2, right? Correct? If you check the curvature of this, and let's say I'm only considering for positive, let's not take the negative part. What is g dash x? It is 3 by 2 x to the power half. And what is g double dash x? It is 3 by 2 into half into x to the power minus half, right? So that is 3 by 4 times 1 by root x, which is greater than 0, right? So it becomes convex, whereas this curve is concave. So if you take a monotonic transformation, the convexity and concavity properties will remain unchanged. Sorry, will change, as you can see in this example. But it's not with the concave, quasi-concavity and convexity. So since fx is concave, that implies it is quasi-concave as well, isn't it? So now we can check if gx is quasi-concave or not. Okay. So how we can do this? We'll take 2 points. Consider a less than b such that root of a less than root of b. So if you take a cube of these, root of a whole cube, that will be less than cube of this. So that means a to the power 3 by 2 is lesser than b to the power 3 by 2. Correct. So this is the condition f of a less than f of b, and this is the condition g of a less than g of b. So what do we check for quasi-concavity of g? It would be g of lambda a plus 1 minus lambda b is greater equals to minimum of ga comma gb. So g of lambda a plus 1 minus g of lambda b is greater equals to g of a. Correct. As ga is lesser than gb, if you take any point in between this range a and b, that would be greater than equals to ga for sure, and therefore gx is also quasi-concave. Okay. If the original function is quasi-concave, then if you take a monotonic transformation, then that also is quasi-concave. So that is preserved under this monotonic transformation. I request all of you to check if gx is quasi-convex as well. Okay. Check if gx is quasi-convex. For that, first of all, you need to check whether fx is quasi-convex or not. If that is the case, then this will automatically happen. Okay. So that's it for today, everyone. With this, we actually complete this topic of quasi-concavity and convexity. So I'm stopping the screen share. Any other questions that anyone might want to ask regarding anything? Okay.
Sir,
Yes, Paramita?
sir, if suppose I don't know how to graphically draw the function, then sir, how can I find quasi-convexity and quasi-concavity? Because we know the formula, sir. If it is convex, then it will be quasi-convex, and if it is concave, we know that it will be quasi-concave. But sir, how to check, sir, for both if we don't know the graph?
Paramita, my suggestion would be, in general,
Mm-mm.
usually the questions or the functions that come are something which you are able to understand. Log, exponent, all these things come. But in case you
Hmm.
don't, the thing that you should do is that you should check with two positive, two negative, one positive, one negative value. Okay, that's a very small trick that works most of the times. All right. Because
Okay,
like
sir.
you saw for the quadratic example, that if you take two positive values, you'll get it. So one example is not enough. If you don't know the graph, then you need to take examples to check that. So examples, not only one, you need to take varieties. So two positive numbers, two negative numbers, one positive, one negative. If these three are done, it's sure. Because if any one of them is not giving you the answer, then you can straight away tell that it's not quasi-concave or quasi-convex. These three would be enough in case you can't draw the graph.
Okay, sir.
Okay. Anything else? Okay. So that's it for today then. Thank you everyone. We can disconnect. See you next week. Bye bye.
Thank you, sir.